Hello, everyone, and welcome to today's reading group, where Snir will be presenting his paper on Weisfeiler-Leman for Euclidean Equivariant Machine Learning. This paper has an interesting take where it takes the 2WL test, which has been very popular in traditional GNN literature, but also applies it for equivariant network and shows like some decent improvement on many different tasks that are relevant to physics. If you want to attend the reading group yourself, you can join us every Monday, and you can subscribe on the link in the description.
So my name is Snir Hordan. I'm a PhD student at the Technion. It's the technological university in Israel, in Haifa city. And this paper is a paper that just got accepted to ICML. It's called Weisfeiler-Leman for Euclidean Equivariant Machine Learning. It's co-authored by myself, by Dr. Tal Amir, a postdoc here, and my advisor, Dr. Nadav Din. And this paper deals with point clouds, right? A point cloud is simply a collection of points in space, right? But it has it's a very common object. For example, molecules, the solar system, many things that we all like to learn using machine learning. And often we would like to assume that it has some geometric symmetry to it, right? So if you rotate a molecule and you apply permutation to the points and translate it, it's supposed to have the same underlying properties, right? Say it's the same underlying phenomenon. So in this talk, we will consider point clouds up to rotations, permutations, and translations. And this will be the topic of how can we achieve completeness? How can we approximate all continuous functions on point clouds using the Weisfeiler-Leman hierarchy? So another important thing that we will use in my paper, it's called the universal property. It's a nice thing from topology. Every invariant function can be seen essentially as a composition of an embedding as a quotient embedding to the quotient space, and composed with a regular continuous function f that we like to approximate using MLPs in machine learning. Maybe now there's the new Arnold Kolmogorov representations. You can use that also. In my paper, I'll do simple MLPs. Okay, and another big theme, as the title suggests, is the Weisfeiler-Leman test. This test is it's a relaxation of the task of graph isomorphism testing. It means that it cannot distinguish among all combinatorial graphs. But it's a very strong relaxation, meaning the graphs that it doesn't distinguish among are very highly regular and not common. So yeah, right now I'm talking about the regular graphs in the combinatorial setting. Soon we're going to make the transition to point clouds. So given a graph with vertices and edges, Weisfeiler-Leman first initializes uniform coloring for each node, right? So it's some feature vector or something like that. And then we iteratively update this coloring via a hash function of the coloring and the current timestamp and the colorings of all of the neighboring nodes. So here I wrote it a little bit differently than usual. Usually what you put here is just the coloring of the neighbors. But it's equivalent to just looking at the colorings of all of the nodes in the graphs, and the delta function being 1 when the node is in the neighborhood of V, if there is an edge connecting it, and if it's 0 otherwise. These are two equivalent representations. We'll soon see why it's important. And then at the end, we get a global graph feature using some aggregation function and hashing the outputs. So Pozniakov was a speaker in this reading group very recently, offered the Euclidean variant of this test, right? Where rather than this delta function, we have the distance, the geometric distance between the nodes. So this actually transfers the problem from a pure combinatorial graph problem to a geometric problem, where we wish to see whether the coloring induced by 1WL completely represents the input point cloud, which is essentially represented by these pairwise distances. So it would be nice if it was. So okay, yeah, this is a nice visualization of what this test looks like by Michael Bronstein. Essentially, each node is characterized by its previous coloring and the number of neighbors and their colors. And it iteratively updates this node coloring until we get a global histogram, which is the final output. If the histogram stops refining itself, so we stop this test. So people looked at this test and they tried to figure out what's the expressive power of this test. So expressive power means what functions can I approximate if I simulate this test, if I replace the hash functions, the combinatorial hash functions, which are usually renewed for each pair of graphs, with global aggregation functions, usually like aggregated sums after applying neural networks element-wise, something like that. What's the expressive capacity? Okay. So in order for it to have complete expressive capacity using the universal property, we need to have a function that embeds the space of point clouds into the quotient space. It's an injective function on point clouds. So, and this was found out to not happen in the case of 1WL. So this is by a paper by Xian Li et al. From Peking University. They show this very nice counterexample where each node has exactly the same distances to its neighbors, and therefore we cannot distinguish among the nodes in these two point clouds. The point clouds are the red points in each figure. And therefore, 1WL will give exactly the same histogram for these 2 point clouds. If you guys know the 1WL test for combinatorial graphs, this is reminiscent of the counterexample for 1WL and regular graphs. We have 2 triangles, and we have a regular figure with 6 nodes, and these 2 are not isomorphic. There is no group action that takes one to the other. So the test cannot distinguish it. So it's not good. So this is why people came and said, all right, how can we improve upon this? So let's use a higher variant of WL. So there is the test called 2FW, 2 folklore WL. I usually call it just 2WL for brevity. And this test does not maintain a coloring for each node. It actually maintains a coloring for edges. So what we do is we initialize the uniform coloring for each 2-tuple or an edge. And then we update this coloring using a different notion of a neighborhood. A neighborhood of an edge is now this term right here. It's the set of this vector containing CTI1J and CTJI2. And this is a more expressive test. It's strictly more expressive. It can distinguish among more combinatorial graphs than 1WL. And recently, it was proven by Del Rosa et al. That this test is complete on point clouds, right? So what does it mean? I take a point cloud, I look at its distance matrix. This distance matrix is essentially some type of adjacency information. It's a complete distance matrix of the point cloud. And then I feed it into the algorithm, into the color refining process of 2FWL. And then I compare the outputs of 2 point clouds when I insert that. It's a delicate point, right? So a point cloud is usually a geometric object, but we look at it as simply a matrix of distances, which is basically a weighted graph which we can then feed into 2WL. So this was proven to be complete. All right, but this is not enough for equivariant machine learning. When you prove completeness of a test, what it tells you is that you can satisfy the universal property, right? So you have an embedding from the space of point clouds to an ambient space, which is the quotient space under symmetries. And then you can approximate any continuous function, any continuous invariant function. But then this is only restricted to continuous invariant functions. This does not give me any guide on how to generate equivariant functions on point clouds. Okay, so what do I mean when I say equivariant functions? An equivariant function is a very common function. It's a function where if I apply rotations, permutations, and translations on the input, and then I apply the function, it's the same as first applying the function and then rotating and permuting and translating the inputs. That makes sense? If you have any questions, if it's not clear, then please let me know. These are very common, for example, in molecular generation, right? If we have some 3D molecule and we want to, we initialize it random, and then we want to get to a conformation. My function has to be equivariant both to rotations, permutations, and translation. Otherwise, it would not be a well-defined function because we're dealing with Euclidean space and isometries over that space of rotation invariance. Okay, so this is where this paper comes in. So we aim to fill this gap. The gap is that right now we only have completeness for invariant functions in point clouds, but we don't know anything about equivariant universality. So yeah, this is an animation of the production of molecular conformation. And this is one of the tasks that I will show. Okay, so let's begin with the main contribution of this article. The first contribution is how do we simulate 2WL just in the pure sense without the equivariance constraint? It's known that there is a very popular architecture, PPGN, by Maron et al., who was a professor here in the Technion, and that showed that you can simulate the combinatorial 2WL for a pair of graphs using this architecture. But this is limited in two ways. And first of all, it's not about, not any instantiation of PPGN can simulate 2WL. You have to learn, the model has to somehow learn using gradient descent or something, how to approximate some symmetric polynomials, and then it will simulate it. And this result only applies for a pair of graphs. So if I feed it a pair of graphs, it will give me different outputs if they're not 2WL isomorphic. What we do is we say, on the entire space of point clouds, using PPGN, we can simulate 2WL uniformly, and for any instantiation of 2WL, for any choice of weights and biases. Okay. The other important result is that 2WL achieves equivariant universality when composed with a simple pooling operator. And I'll show it to you very soon. It's I think it's a very useful result that can be generalized very, very easily to other domains. And lastly, we propose a model, we call it WeLNet, like Weisfeiler-Leman, that is based upon PPGN and the simple pooling operator, and it achieves competitive performance, state-of-the-art performance in both the n-body task and in molecular conformation generation. I'll show it soon. Okay, so the first result is how do we simulate 2WL? All right, we want to, by simulate, I mean replace the hash functions with a differentiable multiset function that will actually embed injectively each aggregation in the test. might be useful to remind you how the test looks like. Yeah, so the test is iterative refinement, right? So we have some coloring at time t, and then we want to get a refined coloring at timestamp t plus 1. In order to do that, we have to embed both the current coloring and some type of aggregation of the neighboring colorings. So how do we injectively perform this, right? So if I have two different neighborhoods, it has to be a different result. And it has to be also permutation invariant because we're dealing with sets, right? So quickly coming back, what Maron et al., Maron and others did is that they made the connection to matrix multiplication and more precisely to tensor contraction. So essentially, if you look at this kind of aggregation procedure, it looks kind of like matrix multiplication, right? If we kind of contract the dimension in the k, denoted by k here, and we sum over scalars that have these values, it's quite analogous. Only here we have some vector representation of two values. Matrix multiplication is multiplication of two scalar values. But interestingly, it can actually work, right? So this is what they proposed. And it's worth looking at, before we show the real results, it's worth looking at how people usually embed multisets, right? Usually, for example, message passing in neural networks, right? You have the neighborhood, you want to embed the multiset of neighbors of each node. What do? You look at, you apply an MLP, right, onto each one of the hidden states, for example, denoted by xi here, and then you aggregate over it, you sum over it, and then you get some vector feature that's supposed to represent the neighborhood of the node you're in, right? And this actual form was proven very recently as injective, right? So if I have two multisets and I have a generic choice of A, then this summation with non-polynomial analytic activation is actually complete, right? So this is a one-to-one function of the space of multisets using just simple MLPs and aggregation. So, but this is a different setting. This is for simulating MPNs, right? What we have is a very different context, like I showed earlier with the matrix multiplication. So what do we have here? We have two matrices with feature dimension, okay? So we store each one of the colorings of each edge, right? We have some initial coloring, and then we refine this coloring. So each coloring can be represented as a feature vector. This is going to be the last dimension, it's going to be D. And we input this into a matrix with a feature dimension. In order to update this coloring information, we apply a neural network onto the feature dimension, right? So we have a matrix, and each point in the matrix, there is a vector. We apply an MLP to each one of these vectors to get a new matrix with a feature dimension with a refined representation of each vector. And we do this twice to the same feature, the same matrix. And then what do? We just perform matrix multiplication along the feature dimension. What it looks like essentially is just entry-wide multiplication and summing along the dimensions of the matrix, right? So this is standard matrix multiplication performed in parallel along the feature dimension. This is a little bit complicated. If you have questions, feel free to let me know. But this is the function we have to show that is injective. It is actually one-to-one. What we show is that for almost any choice of parameters, right? You don't have to learn it. It's just the pure random choice of parameters. xij out, right? This matrix, right? This is the entry of the matrix, but x out, not xij out. X out is an injective embedding. No, okay. Xij out is an injective embedding of this multiset, right? This is what we want to show. So xij out is an injective embedding of the update step of 2WL. This is not a trivial result. It's based on some phase reconstruction result and functional analysis, stone partial, stuff like that, and to show that this aggregation procedure actually is an embedding of this multiset. Right. So any instantiation of PPGN, but it has to be with analytic, non-polynomial analytic activations. Right. So, for example, ReLU will not work here. Right. So in the famous how powerful are graph neural networks, they show the counterexample why this wouldn't work. Yes. So, and also another point is that there are other ways to simulate these steps by Jogel et al., but they require a qualitatively higher computational cost of quadratic of n to the fourth cost versus our cubic. Okay, great. So now we will look at something that may seem unrelated, right? So now we will go into the equivariant functions and discussion. And we have a completely different result. It looks different, but very soon I'll show how it relates to 2WL. So equivariant GNNs perform aggregation over vectors. You have a point cloud, time t, and you want to compute the coordinates at time t+1. It's very popular, extremely popular. I'll show soon the papers that do this. To just look at a weighted aggregation of the vector differences of the other vectors in the point cloud. A lot of the popular graph neural networks use this representation. And the standard form is for a shared function g, which is a function of xi, xj, in all of the other points. For each entry I in the function. And right, so just to remind you, f is a function from a point cloud to a point cloud. So from a matrix, 3 by n matrix to a 3 by n matrix. And what we show here for the first time is that this form of aggregation is actually complete. That's all you need to approximate all equivariant continuous functions on point clouds. So yes, like I said, an abundance of equivariant GNNs use this aggregation procedure with various choices of the weighing function. So for example, if we were to look at the hidden states of the neighboring nodes and the distance from the ith node to the neighboring nodes, that would be exactly in the form I wrote above. There are many examples that implement this. So for example, eGNN, PAIN, DGSM, ConfGF, these are widely used networks with hundreds of citations, and they perform this aggregation procedure. You can also do other things. G can be even a transformer co-joined with the distance matrix. And this is also a choice of G, which was performed by Unimod. Yes, but none of these are known to be universal, right? So these are not known to be universal models. And in many instances, I can prove they're not universal. But what we do is that we actually show that universality can be achieved. Okay, so how does this relate to 2WL, right? So 2WL, right? It's a process where we take the input point cloud, we look at its distance matrix, And then we feed this distance matrix as the edge information of 2WL, right? So if we look at the edge features along the refinement process of 2WL, we can actually extract these edge features and plug them into a function h, which will take them as inputs, and then we can perform aggregation using these edge features. So how do we do this? We first prove that after 5 iterations of 2WL, each edge feature is a translation and orthogonal invariant embedding of the vector multiset xi, xj, and the set of the other points. All right, so this is it's a very important result that was not shown yet. What was shown in the past was just that you can get some global graph feature. But here what we show is that using 2WL, we can get an equivariant feature for each edge of the point cloud, for each 2 points in the point cloud, that completely determine both the 2 points and the other points in the point cloud. And what we also showed is that in theory, this representation for some choice of feature of C5ij should be a universal representation. And if we use this embedding that comes out of 2WL, this is actually a universal representation, right? So this very simple aggregation procedure of just looking at the sum of the vector differences can actually approximate all continuous equivariant functions on point clouds, right? And it's an interesting thing to note if you're looking at this, that any replacement of the C5ij by an injective embedding of xi, xj, and the multiset will be sufficient for universality as well. So essentially presented a framework for proving universality. Okay, so now what's often not discussed about in literature is that many times we learn functions that have velocity information as well, right? So for example, the n-body problem is essentially a problem where you have different particles in space, you have their velocity, you have their position, and you have some interaction between them, for example, some magnetic interaction, and you want to predict the trajectory. So many times you have this velocity information, you want to incorporate it. So what we show is that using 2WL, we can modify the input into 2WL. So it will not just be a regular distance matrix. It will actually be a matrix with a feature dimension. And along that feature dimension, we will actually have not just the distances among the points in the position point cloud, we will have another point cloud with velocities. And we have to incorporate the distances between the positions and the velocities in order to achieve completeness using 2WL. Yeah, it's a non-trivial result that is not obvious. For example, if we were to remove the distances between xi and vj and vi and xj, this would not work because you could have a velocity point cloud and a position point cloud that will give me the same output for 2 different pairs, but they might not share the same rotation. So it may be that one velocity point cloud is equivalent to the other, but their positions are not, or they're related by a different rotation. So we also incorporated this. Right, and xic is just taking each coordinate and subtracting the center of the point cloud, so the mean of the positions of the point cloud. And yeah, this is actually also the first time that it was shown that velocities can also be introduced inside the network and can also be achieved universality, not just in the position. Okay, great. So right now we looked at all the theory and how 2WL and equivariant functions connect to each other. Now we introduce the architecture that we built upon these results. Yeah, so okay, so our architecture is called WeLNet, right? So it's the Weisfeiler-Leman test. The Weisfeiler-Leman test inspired the network. And it's essentially a successive application of Euclidean Equivariant convolution layers. We initialize noise-wise hidden states. And we have a shared 2WL equivalent analytic PPGN architecture. So analytic meaning the actual activations are non-polynomial analytic activations. And then we perform some convolution. This is just the implicit convolution. First, now I'll show what it looks like. We perform this convolution at each step, and we do this for a few steps. So what does it look like? Yeah, so we essentially infuse PPGN and EGNN, equivariant graph neural networks together. And we get a new architecture. So what do? We first of all apply PPGN on the input point cloud. We get a matrix of vector features. And then we incorporate this matrix inside the classical Euclidean message passing procedure. So this PPGN architecture actually gives us edge features we will use as edge features in the EGNN backbone. So each neighbors will have a feature that comes from the 2WL test. And then we perform standard message passing that's performed by EGN, sorry. And if you can look at here, this relates to the theoretical results. We have some psi of x, which can approximate any continuous function. We have Mij, which contains the edge feature from 2WL, which we showed is complete on point clouds. And then we incorporate this into the aggregation, which is exactly that aggregation that I showed earlier that we proved is a universal approximation of all equivariant continuous functions. And this is provably a universal architecture using only 2WL and standard Euclidean message passing. And I would note that this is very different in many approaches in literature. And the aggregation is very common, this type of aggregation, but many times there's another type of very common aggregation procedure, which is looking at irreducible representations of SO3. Taking a point cloud and looking at Kronecker products of the point cloud. Probably many of you know this, and then kind of looking at the irreducible representations under SO3 of these tensors. This is a very heavy computational load. And what we do here is that we completely bypass that to achieve universality, right? All of the tensor field networks, many other GNNs, all of these networks use these irreducible representations. Also, torsional diffusion uses it. So we show, and these are known to be universal. So it was proven pretty a while back ago, like 2021. But those are universal architectures for large enough ambient dimension. Actually, for an arbitrarily large ambient dimension, it has to be infinitely large. And what we do here, we completely bypass that using only the distances of the point cloud, only distances and vectors, and we completely achieve. We provably achieve universality. Okay. Okay. Yes. So let's look at the fun side of the paper.
Just a clarification on the previous slide. What's why the convolutional or the MLP layer there? Yeah, phi of h.
Yes, this one. Yeah.
Yeah.
You're saying, why do I need this?
Yeah, yeah.
Yeah, so phi of h is essentially, it's like a standard, like a message passing framework type of update. So MI kind of contains all of the messages from all of the neighboring nodes. And then I update my node using my current value and the messages coming from the outside.
Ah, okay. Thanks.
Yes. Thank you. Yes. Yes, this is equivalent to this falls under the message passing frame, but only in the Euclidean setting where we don't only update the hidden state, we also update the position.
Mm-hmm.
Okay.
Yeah.
Yeah. So the experiments now, the n-body problem is a very well-known problem. I'll describe it briefly. It's 5 particles with electrical charge that go off in a trajectory. So as well known from physics, there's no closed form solution to the n-body problem, right? It's a chaotic system, and a very small change in the initial conditions will set it wild. It can be simulated using an ODE solver if the initial conditions are very nice, but there is no closed form solution, so this is why it's interesting for machine learning. Also, the simulations are quite costly, both in time and compute. And this is exactly an equivariant task, right? So what we do is we want to compute the trajectory of the particles under their pairwise interaction, under their effect on each other with magnetic force. So we applied WeLNet on this very well-known problem. We got a nice result. So it's a non-trivial improvement by 10% from the very recent, transformer PS model, which had a state-of-the-art result very right before us. And it shows that we do not need to use irreducible representations and very complicated group representation theory models in order to get good performance. So, for example, SEGNN is a type of model that uses these irreducible representations. And we have some other models. So transformers, obviously, transformer PS uses transformers. This shows that our universality result actually holds water. Okay, we also tested our architecture on the n-body problem, but with external forces. So what it is now, it's all these particles, but there is some gravity force field or some magnetic outside magnetic forces applied on the particles. So it's a very interesting results, because in the gravity, when we have an outside gravity force field acting on it, WeLNet and other architectures perform very well. But under an external Lorentz force field, magnetic force field, all architectures just go crazy and they don't work. Theoretically, it's fine because we're not universal on functions with external forces. It's only on functions on point clouds that all of the information is contained in the point cloud. But this is, I think, it's an interesting direction for further research, because this is not, there are no real good results on this data set. Okay, and the more, another practical data set is confirmation generation. So what we look at here is that we're giving some molecular information of the data set of molecules. It's a graph with the atomic numbers of the atoms and their interconnectivity via their chemical bond, right? So we have an edge between two nodes in this chemical graph if there is some chemical node between them. And we also have the chemical bond information and other chemical information that I'm not an expert on. And what we do is we try to recover a position representation of this molecule. So what's the positions of the atoms such that this molecule is at a local energy minimum. This is what it looks like in nature, and then I can actually study different properties of this molecule and use it for downstream tasks like property prediction and stuff like that. Yes, probably Hannes and Dominic are very familiar with this, obviously. So this is what it looks like. This is a simulation of it. So we start off with random noise. And then our model is the little time steps. It kind of predicts the direction of where the molecule should go to be in this energy minimum. Yes, thank you for for this animation. Right, so we tested it on the GeoMQ9 data set. It's a very popular data set. And we have comparable results in the coverage metric. It's essentially a metric that measures the diversity of the confirmations. So how many confirmations are within some radius of the ground truth global minimum. And we have a new state-of-the-art result. It's a nice improvement of about 15% from the previous state-of-the-art on the matching score, which essentially measures how does the best confirmation, the confirmation with the minimal distance to the reference confirmation, perform. So I think the main takeaway is that the generalization of our model may be only competitive and not the best, but in terms of approximation power, it looks like the universality guarantees allow it to get this minimum confirmation that is very close to the reference, but it does not generalize well among all of the confirmations that it creates. Yeah, so right, so on this point, so we don't we have this result that kind of shows that we have good approximation power, but we're not sure that that it generalizes the best. It may generalize much better. So the main future direction is that we have to make this scalable. Like I said earlier, the time it takes to simulate 2W using PPGN is actually cubic time, right? And this is not desirable. This is not the desideratum in machine learning. We want something to run in linear time. We're very, we want to scale. What we can do is that we can relax the completeness assumption with a more relaxed completeness condition by looking only at the matrix of distances that we feed into 2WL, but with the distance cutoff. So we have the notion of a neighborhood, and the number of edges in this matrix will now be linear in the number of points, if not quadratic. And we can also impose a sparse variation of 2WL, which runs in linear time, the number of nodes. And this may improve generalization. And obviously it will improve running time as well, which will make it more scalable. Another very important direction is integration into diffusion flow matching training, right? So the way I trained this, I didn't mention it, but we trained this using score matching. And this is kind of an outdated method. It works well, but it's kind of outdated. Usually now, flow matching is more popular in Fusion. And I think that the inherent structure of 2WL can be leveraged in this process by looking at, for example, 2WL can count triangles, right? That 1WL cannot. And we can use this information in order to create a custom flow matching objective. And just the fact that all of our information is contained in the distance matrix is also interesting. There are natural symmetries to the distance matrix that we can leverage. And these are two the big directions that I think can highly improve this model. And yeah, these directions is always with the guarantee of universality, which is very important. And I think in general, it's important for the community to kind of prove or show that their model is universal, right? So it's usually very loose, the way people in the community do it. They kind of say, okay, it's time limits. If we look at an arbitrarily large dimension of ambient space, it will be universal, but in practice, it's usually, there's no such guarantee. Here, we actually give a concise way of showing that every instantiation of the model is complete, and the aggregation procedure is universal, and our model in practice can approximate these functions. And this is something that I think is a good idea to apply for other architectures. And yes, this is the end of the talk. So yeah, thank you for listening. And if you have any questions, please let me
know. Hello.
Hello.
Yes. Thank you for the talk. I just have a question. So all these proofs or completeness for both your talk, I mean, the paper you just have presented, and for the one you mentioned it at the very beginning about invariant functions. So yes, both these papers prove completeness of the corresponding WL test and like matching architectures for finite point clouds. So can you say like something about like 1D, 2D, or 3D infinite crystals? So is there any analogous proof of completeness?
Can you repeat it? What did you say about the D?
So imagine, let's say, three-dimensional crystal. So three-dimensional crystal, you can think of it as just some atoms inside the unit cell, which are infinitely repeated, like up, down, left, like back and forth. And now you have like two three-dimensional crystals, also like consisting of like point viewpoints. And do you have any proof, or maybe vice versa, a counterexample that these machineries, like, are they complete for such infinite point clouds or not?
Okay, I see. So you're saying, yes, thank you for the question. Yes, so you're saying if I have some type of infinite crystal with some type of symmetry that just keeps on repeating forever.
Yes, exactly.
Okay, yes. Okay, yes, this is a great question. And yes, obviously. Yeah, so I think that I agree. This is a limitation that we're only looking at finite point clouds. And obviously, you're familiar with the work of Curlin, and that looks more into these crystals. I think it's an interesting. You're saying, how do we define? Completeness. Right. So I think that I agree that the result on invariant completeness is just by Del Rosen, and this is another result. And this result here is derived from that, and it's a custom result that doesn't look at the final output. It looks at the colorings along the way of the 2W iteration, and then looking at the edge features. So these are kind of equivariant features. It only applies in the setting of Del Rose, which is a finite point cloud. And yes, this is I agree. This is the limitation. Yes.
Yeah, probably might be an excellent gap in the current literature for the future research. I think it is quite relevant for the field of atomistic machine learning and for machine learning interatomic potentials.
Yes, I agree. Yes, thank you for that comment. I agree. It's a great question for future research. Yes, if we can define, and even more to define all of the equivariant functions on these, on these crystals,
And sorry, do we have couple of minutes? Okay.
Yes.
I just wanted to send you probably, I don't know if you already citing this paper in yours or not, but I believe that this paper might be relevant. So it is basically a methodology about constructing machine learning interatomic potentials. It is similar to your work in a sense that it also accounts for vectors associated with each atom. And the methodology is simply constructing all the possible equivariant polynomials and next doing a linear regression. So I guess there might be some very, very nice connections between your WL test and between your architecture and this work. So probably there might be some mapping, probably I don't know, n layer of your architecture can produce some polynomials which are discussed here. So it is just a comment.
What is this paper that you mentioned?
I sent you in Zoom chat.
Okay. I think in general, your point about polynomial is very interesting. I think that, like I mentioned, the universality results of my advisor, Nadav Dim, usually looked at approximating high-order polynomials. And I think this paper is kind of a departure from that perspective, but I do agree that it's not clear how the two approaches converge. What's the relation between this polynomial approximation and the universality result that is more geometric in proof? And I agree. It's a good point actually to study that.
Yeah.
Yes. Thank you.
Yeah. Thank you for your answers. Probably I'm done.
Just a quick query here. So, do you have a code available, and did you use CUDA kernels to code it, or just Python?
Yes. So we have the code available, and I can send it in the. It's in the. Okay. I'll upload a new version of the paper soon to archive, and it will be there. But I can also just send it in the chat. And what was the second question? If I used PyTorch?
CUDA kernels here.
CUDA. Yeah. Everything runs on GPUs, CUDA, and with PyTorch.